Hey guys, in this video I'm going to discuss two questions. The first question is going to be on continuous random variables, mainly a two variable question, and the next question will be on uniform random variables, right? So let's just start. So the first question says that, the joint probability density function of a two-dimensional random variable x comma y is given by, this is a two-dimensional random variable, right? So this is the joint probability density function, where my x lies between 0 and 1, and my y lies between 0 and x. My y lies between 0 and x, right? And it is 0 elsewhere. Right, so this is elsewhere. So the first part says that find the marginal density functions of x and y. Marginal density functions of x and y. Therefore we need to find f of y and f of x. The second part says that, or let me just solve the first part first, right, and then we'll write the second part. So we need to solve the first part. So our fx comma y is just 2, right, where my x lies between 0 and 1 and my y is lying between 0 and x. This is my joint probability density function, and I need to find the marginal density function. Yes, so now we need to find the marginal density. We need to find fy and fx. So let's just find fy first, right? We are given that x lies between 0 and 1 and y lies between 0 and x. Now the formula says that for finding the marginal density of y, we need to put in the limits of x and we need to treat y as a constant, right? So if we have fx comma y, this joint probability density function, we need to integrate this function using the limits of x, and we need to treat y as a constant. Why? Because I'm writing dx here, right? So fx comma y dx, we are integrating this function over x, right? So we treat y as a constant, and this is minus infinity to infinity. I'm just writing this if my x lies between minus infinity to infinity, right? So now we need the limits of x for finding f of y, and x lies between 0 and 1, right? But here it is written that y lies between 0 and x. This means that y is less than x, right? So from this and this, can I conclude that x lies between y and 1? Because see, x is always greater than y. X is always greater than y. And x is less than 1, right? So can I write the limits of x as x lying between y and 1? I can. From y and 1. See, the reason why I'm not using 0 here, right? This is because I need to find the marginal density function of y. My main aim of doing this is I should get a term from fx comma y which is independent of any variable x. So the term that I get in the end, fy, the marginal density of y, should be independent of any other variable, right? So the term should only comprise of having one variable, that is y. Then only I can say that I have a marginal density function of y. This is the reason why I am including y in the limits. and we also need to make sure that we don't miss any term of y, right? Because we are finding f of y. This is also one more reason why I have to include that in the limits, right? So now 2x 2 dx, right? 2 dx, 2 was my joint probability density function. If I just show you guys, see, so if x comma y is equal to 2, right? So if I just integrate this function, I'll be getting 2x, and my limits of y are y and 1, right? So I don't have any y term in 2x, right? If I would have integrated this function from 0 to 1, 2x dx from 0 to 1, I would be getting 2x, and my limits would have been 0 and 1, right? So when I substitute the limits 1 and 0, I'll be getting 2 only. See, and in this term f of y equal to 2, let me just show you guys. For example, my limits were from 0 to 1, and this is 2 dx, right? So I'll be getting 2x, and my limits will be 0 to 1, and this will come out to be 2, right? But this is incorrect. I don't have any term of y here. So how can I say that this is f of y, or the marginal density of y? I cannot. And this is actually equal to joint probability density function only, right? So how can we say it is equal to the marginal density of y? We cannot. This is the reason why, to not miss out on any term of y, we need to include it in the limits, right? But if my limits were just like x lies between 0 and 1, and y lies between 0 and 2, or y lies between 0 and 1, then I won't be including y in my limits. But if I have a scenario where I have x lying between 0 and 1 and y lying between 0 and x, I need to include the term of y in the limits, so as to not miss any term that I get finally in my marginal density function. Hence, what I'll be getting is 2 1 minus y, right? So my f of y after putting in the limits becomes 2 into 1 minus y, right? And I'll be drawing a box. So for fx is equal to now dy integrating this function over y, because we are finding marginal density function of x, and now my limits will be, my x was lying between 0 and 1, my y was lying between 0 and x. From this I can deduce that my y lies between, for f of x we need to put in the limits of y, right? So I can conclude that my y lies between 0 and x, right? So my limits of y will be 0 to x. So this will give me fx is equal to 2y lying between 0 and x, which will give me 2x. Therefore my fx is equal to 2x. Let me just check if what we are doing is correct. From the book, fx is equal to 2x. So f of y was 2 into 1 minus y, and fx was 2x, right? So let me just check. Yes, we are right. Also my x will be lying between, my x lies between 0 and 1, and my y lies between 0 and 1. Why? Because the maximum value of x can be 1, right? If we see here, the maximum value of x can be 1, so my y can lie between 0 and 1, and same goes for my x, right? My x lies between 0 and 1. Yes. So now the second part says that find the conditional density function of y given x is equal to x, and conditional density of function of x given y is equal to y. So we need to find conditional density function of y given x is equal to x. So we need to find fx is equal to x, right? Therefore what we need to find is fx comma y divided by f of x, the marginal density of x, right? So we know that our fx comma y is equal to 2. Therefore, and we also found our fx was equal to 2x, right? So my f of y conditional x will finally come out to be 1 upon x, right? So my f of y is equal to 1 upon x. I'm just using the formula of conditional probability, right? So this is actually equal to fx is equal to x intersection y is equal to y divided by f of x, right, which is equal to f of x comma y, right. So this is our fy conditional x. Now we need to also find our f x conditional y, right. So our f x conditional y is equal to x intersection y is equal to y divided by f of y, which is equal to f x comma y divided by f of y. R f x comma y is equal to 2, R f of y is equal to 2 into 1 minus y, and hence we will be getting 1 upon 1 minus y f of x conditional y. Therefore our f x conditional y is equal to 1 upon 1 minus y. Let me just check. 1 upon x and 1 upon y. 1 upon 1 minus y. There. So I need to write the limits also here, right? So for f y conditional x, I'll be writing the limits of y, and that will give me y lies between 0 and x. Whereas for my f x conditional y, my limits of x will be where my x lies between y and 1. Now we need to find our third part. Right? Our third part says that. My third part says that check for independence of x and y. Check for independence of x and y. So f x comma y is equal to f x into fy. This is the condition that we need to check. Rfx comma y was just 2. Rfx was let me just check again. Rfx was 2x and our fy was 2 into 1 minus y. 2x into so fx was 2x. F of y was 2 into 1 minus y. This gives me my fx into fy. This gives me my fx into f of y as 4x into 1 minus y. And this means that my fx comma y is not equal to fx into fy, therefore not independent. Why? Because my fx comma y, which is the joint probability density function, was not equal to the product of the marginal probability densities of x and y. Yes, we are right. Now this was a very easy question. Now we are moving to the next question. Question 2 that I'll be taking today is this is done. This question was done. Let me just keep my book. So the next question says that consider independently and identically distributed random variables. So consider independently and identically distributed random variables. Consider IID variables. Consider IID random variables. Consider IID random variables x1, x2 till xn. These variables are identically and independently distributed. IID random variables, independently and identically distributed random variables with values in 0 and 2. Let me just write this again. Consider IID random variables x1, x2. We have n random variables x1, x2, xn, and all of these variables have values between 0 and 2 with values. Consider IID random variables, independently and identically distributed random variables x1, x2 till xn, who have values between 0 and 1, where xi belongs to 0, 2, I lies between 1 and n, right? So I is equal to 1 comma 2, comma 3 till n, right? So I can take values n, right? So you have n random variables, identically and independently distributed random variables, and each x lies has any value between 0 and 2. Each of these random variables, yes, so each of these random variables are also uniformly distributed on 0 and 2. So consider independently and identically distributed random variables x1, x2 till xn with values in 0, 2. Each of these random variables xi is uniformly distributed between 0 and 2. Yes, between 0 and 2, uniformly distributed on 0 and 2, where I is 1, 2, 3 till n. Yes. Now, if y is equal to max of x1, x2 till xn, then the mean of y is, so y is a variable which is the max of all of these values x1, x2, xn. So the max of this is y, and we need to find the mean of y. So basically let me just explain you the question. X1, x2, xn, all of these variables are independently and identically distributed random variables. Are IIDs. We refer to them as IID variables. And each of these variables are uniformly distributed on 0, 2. Now we need to find the mean of y, where my y is the max of all of these variables. I have also discussed one max min question on my channel earlier. You can refer to that question, it will help you a lot, right? And I need to find the mean of y. And I have been given the options. The first option is n upon n plus 1 whole square. The second option is n upon 2 n plus 1, and I have all of these 4 options. I have 4 options being given, right? And I also know the correct option here, so I'll just check and prove. So we need to prove, or let me just write the solution. Let me just write the correct option. We need to prove that the value of my mean is. Let me just make this as a proof question. We need to prove that mean of y is equal to 2n upon n plus 1. Right? We need to prove that. Let me just make this as a proof question. Prove that mean of y is equal to 2n upon n plus 1. So I'd be given 4 options, and I just wrote the correct option, and we are just going to prove this. Prove that mean of y is equal to. Prove that mean of y is equal to 2n upon n plus 1, where y is the max of all of these variables, and each variable x is IID variables, which is uniformly distributed on 0 and 2. So let's just find the CDF of y. I'm saying that I've discussed the question on max and min in my previous video, one video, CDF and solving maximum PDFs. Just refer to that video, it will help you a lot. Yes, otherwise you won't be able to understand this much, but it is a very easy process that I always follow. We just have to find the CDF first. We'll be finding the CDF first, then we'll differentiate it to find the PDF of y, and then we'll just apply the usual process of finding the mean of a continuous random variable, which is y into probability of y, or y into PDF of y, and integrate it over the limits of y, and be getting the values. So now we need to find the CDF of y. The formula for CDF is y less than equal to small y. Yes, and y is max of all of x1, x2, x3 till xn less than equal to y. The max of all of these values is less than y. This means that if the max of all of these values is less than y, then individually also all of these x's, x1, x2, xn, individually also all of these variables are less than y. Therefore I can say that x1 is less than equal to y, x2 is less than equal to y, x3 is less than equal to y, and so on, xn is less than equal to y. I can say that because the max of all of these values is less than equal to y. So individually also, for example, if x2 is the max of all of these values, x2 is the max of all of these values, right? This means that x1 is less than x2 and x2 is less than y, because x2 will be equal to y. If I have y and I have all of these values till xn, right? And the max of x1, x2 till xn, this is equal to x2. x2 is the max of all of these values. For example, x2 is the max of all of these values. This means that y is, we can write y as y greater than equal to x2, right? Because greater than equal to x2 satisfies the equation, because y is actually equal to x2, so y greater than equal to x2 also satisfies, y being equal to x2 also satisfies this inequality, y greater than equal to x2. And now x1 is less than x2, x1 is less than x2, right? So I can write that y is greater than equal to x1 also, because x1 is less than x2. That is what we are doing here. I'm writing probability of all of these variables being less than equal to y. And now because these are IID random variables, this means that I can write their probabilities as x1 less than equal to y intersection x2 less than equal to y intersection x3 less than equal to y till xn intersection xn less than equal to y. But these are independent random variables, so what I can do is x1 less than equal to y intersection or for example the product of all of these values, x1 less than equal to y into probability of x2 less than equal to y. This is property of independent random variables, right? So x3 less than equal to y till probability of xn less than equal to y. Now any xi less than equal to y is basically the CDF of x, right? And we know that xi is uniformly distributed between 0 and 2. So what is the CDF of x, xi, where my I lies between 1, 2, 3 till n, right? So my CDF of fx is, the formula for CDF, for calculating the CDF of uniformly distributed random variables, is 1 upon 2 0 to y dx. Why am I writing 1 upon 2? Because the property of uniformly distributed random variables says that the PDF of a uniformly distributed random variable will always be equal to f of x will always be equal to 1 upon b minus a, and where b and a are where my x lies between a and b, right? So here what happened was, my b was equal to 2 because my xi was lying between 0 and 2, right? So my PDF will become fx, and the formula for calculating a CDF is the formula for calculating a CDF is just integrate the PDF over the limits for which we are trying to find the CDF, right? So finally my CDF of fxi becomes, my CDF of fy becomes fx1 fx2 till fxn, right? The product of all of the CDFs. This gives me, and my fxi was 0 to y, or my fxi which is equal to probability of xi less than equal to y equal to 0 to y 1 by 2 dx is equal to x upon 2, and my limits are from 0 to y, which gives me y by 2. My fxi is equal to y by 2. Therefore my f of y becomes the product of y by 2 n times, because we have n random variables, right? I lies between this I, fxi. I is denoting the I in the superscript is denoting the number of xi's, right? Sorry, in the subscript, not in the superscript. I'm very sorry. So yes, what did I write here? I just forgot. Yeah, so my I lies between 1 to till n. Right. Now we have gotten the CDF of y. CDF of y was probability of y less than equal to y. So this is the CDF of y. For finding the PDF of y, what I'll be doing is I'll be just differentiating this function. So f of y is equal to 1 upon 2 to the power n into y to the power n. So my PDF of y will become f of y, and differentiating this term will give me n upon 2 to the power n, because 2 to the power n is a constant, so it will remain as it is, and y will become y to the power n minus 1. Yes, and now for finding the CDF, for finding the mean of y, what I need to do is I need to find E of y. E of y is basically the mean of y. You can check my videos, earlier videos, if you have any doubts regarding this. E of y, and the formula for E of y is y into the PDF of y and the limits of y. Right, now my x lies between 0 and 2, my xi lies between 0 and 2. Then the max of all of the x are lying between 0 and 2. So the max of all of the x who all are lying between 0 and 2, the max of all of these values can be any value lying between 0 and 2. The max of all of the values that are lying between 0 and 2, the max of all of these values, which is y can also lie between 0 and 2 only. Right, so my limits for y will also become 0 and 2. So y into the PDF of y dy. Right, and my PDF of y was 0 to 2. My PDF of y was n by 2 into y to the power n minus 1 dy. Right, so this gives me, and this was 2 to the power n, right. Let me just show you guys. This was the PDF of y. N upon 2 to the power n, y into y to the power n minus 1. This gives me n upon 2 to the power n comes out because it's a constant term. Finally, what I have inside is 0 to 2. Now y into n minus 1 gives me y to the power n dy, right, and this gives me, after integrating this becomes n plus 1 upon n plus 1. And my limits for y are 0 to 2, and this was a constant term, n into 2 to the power n. Finally what I have is, after putting in the limits of y, I have is the E of y, or the mean of y. The mean of y is n upon 2 to the power n into y into 2 to the power n plus 1 into 2 to the power n plus 1 minus 0 to the power n plus 1 is 0 only, and I have n plus 1, which is a constant term in the denominator. So finally what I have is n upon 2 to the power n into 2 to the power n plus 1 divided by n plus 1, which gives me 2n upon n plus 1. So my EY, or my mean of y, is equal to 2n this 2 to the power n plus 1 gets cancelled from 2 to the power n, and I'll be left with 2 only in the numerator, and I also had n in the numerator along with the denominator n plus 1. So finally my mean of y comes out to be 2n upon n plus 1. Let me just check if what we've proved is right. Prove that the mean of y is equal to 2n upon n plus 1. See, if you have any doubts regarding this, you can check my video out where I've discussed the CDF and solving the PDF of max and min. The video is finding cumulative distribution functions and solving max min PDFs. Check that out and then come back to this video if you have any doubts. and everything will get cleared. It is very basic what I've discussed here, right? So thank you so much, and I'll see you in the next video. Bye bye.